Welcome to the chapter on advanced process control. This chapter is crucial for chemical engineering students as it covers essential control techniques to ensure industrial processes operate efficiently, safely, and within specified limits. In this chapter, we will cover process dynamics, control systems, and instrumentation. These topics are fundamental for designing and implementing effective control strategies in chemical engineering. Process dynamics involves studying how process variables like temperature, pressure, flow rate, and concentration change over time in response to external inputs or disturbances. Understanding these dynamics is essential for designing effective control systems. One key concept in process dynamics is the time constant, denoted by the Greek letter tau. The time constant characterizes the speed at which a process responds to changes. For a first-order system, the relationship between the input and the output can be described by the differential equation. Tau times the derivative of y with respect to time plus y equals k times u. Here, tau is the time constant and k is the process gain. Consider a tank of water being heated by a steam coil. The temperature of the water changes over time in response to the steam flow rate. Assuming the system behaves as a first-order process, the temperature response can be described by the equation tau times the derivative of t with respect to time plus t equals k times f sub s. Here, tau is the time constant of the heating process, and k is the gain relating steam flow rate to temperature change. Control systems are designed to maintain process variables at desired set points despite disturbances. There are various types of control systems, including feedback control, feed-forward control, and advanced control strategies. Feedback control involves measuring the process variable, comparing it to the set point, and adjusting the control input to minimize the error. This is a common method used to maintain desired process conditions. A PID controller adjusts the control input based on the proportional, integral, and derivative of the error. The control law is given by U of t equals k sub p times E of t plus k sub I times the integral of E of t with respect to t plus k sub d times the derivative of E of t with respect to t. Here, U of t is the control input, E of t is the error, k sub p is the proportional gain, k sub I is the integral gain, and k sub d is the derivative gain. In a chemical reactor, maintaining the temperature at a desired set point is crucial for optimal reaction rates. A PID controller can be used to adjust the heating or cooling rate to keep the reactor temperature at the set point. Instrumentation involves the use of sensors and actuators to measure and control process variables. Accurate and reliable instrumentation is essential for effective process control. Sensors are devices that measure process variables such as temperature, pressure, flow rate, and concentration. Common types of sensors include thermocouples, which measure temperature based on the voltage generated by the junction of two different metals. Pressure transducers, which convert pressure into an electrical signal, and flow meters, which measure the flow rate of liquids or gases. Actuators are devices that adjust the process based on control signals. Common types of actuators include control valves, which regulate the flow of fluids, pumps, which control the flow rate of liquids, and heaters, which adjust the temperature of a process. In a pipeline, maintaining a constant flow rate is important for process stability. A flow meter can measure the flow rate, and a control valve can adjust the flow to maintain the desired rate. Advanced process control is a vital part of chemical engineering that ensures processes operate efficiently and safely. Understanding process dynamics, control systems, and instrumentation is essential for designing and implementing effective control strategies. By mastering these concepts, first-year chemical engineering students will be well-equipped to tackle more complex control challenges in their future studies and careers. Thank you for watching this chapter on advanced process control. We hope you found it informative and helpful. Stay tuned for more topics in chemical engineering.